Hello everyone, welcome to lecture 34 of the online course on Introduction to Microwave and Optical Metamaterials. Today's lecture we will be looking into metamaterial-inspired antennas. So this topic will be taking 2 lectures, so that is why this is the first part of it. So in this we will cover first about a 2D model of microwave antenna with 2-layer metamaterials. So this is an extension of the 1-layer wire composite structure that we have seen in the previous lectures, and then we will take up some topic of antenna miniaturization with metamaterials. So let us focus on this 2D model of microwave antenna that has got 2-layer metamaterial. So in the previous lecture we discussed the 1-layer wire composite structure, mainly as a substrate for a patch antenna, and finally we have also seen that putting a magnetic superstrate helped improving the antenna characteristics. Now a normal extension to this work would be to try 2 layers of non-magnetic metallic wires which are symmetrically embedded within the host dielectric substrate, and then again evaluate the antenna characteristics using the same parameters or metrics that we done for this 1-layer case. So I will not repeat those calculations again, but I will just show you that if you consider different designs like the standard antenna with a dielectric substrate and no superstrate, in that case if you compare the 3 or 4 performance metrics like the resonance frequency, efficiency, the maximum directivity, and the percentage gain, you can actually see that your standard antenna, the resonance frequency is around 7.3, efficiency is 40.72, and Dmax is around 4.6 dB. If you replace the dielectric substrate with a 1-layer wire grid, it is not exactly replacing. You can say if you put a 1-layer wire grid structure into the dielectric substrate, that basically increases the frequency a little bit, but on the other hand also increases the efficiency and the directivity, right. So that is a good improvement. Now if you go for a miniaturized antenna with the same 1-layer wire grid but without any superstrate, you see the frequency gets further increased, efficiency also increases as you can see here along with the directivity. So that is a positive move, right. And then if you try to introduce superstrate on this standard or like this one here, if you have 1-layer grid structure but the standard antenna and then you introduce the superstrate, you will see you can actually compare these two. So the frequency slightly reduces, the gain or efficiency slightly increases, same for the directivity, right. And if you try the same thing on the miniaturized antenna with superstrate, you can see the frequency is around 7.4, the efficiency further improves. So that is a good thing, you can compare this to this, and then finally you can get the maximum directivity, that is 6.59 dB, right. So that is all the cases that we have done for 1-layer grid. Now I am not showing the results, but I can show the parameters that we obtained for 2-layer wire grid structure. You can see that the frequency comes around 7.518. So the frequency slightly increases. This is for the standard antenna without any superstrate. So you can actually compare this one along with this one, that is why they are painted in the same color. So what you see that from 1-layer to 2-layer there is not too much increase in the efficiency nor in the directivity. So what you can conclude that adding multiple layers of this kind of wire array to the composite substrate does not really provide much significant improvement in the antenna characteristics, right. So if you carefully look into this table, these are the conclusions that can be drawn. So you can see that the miniaturized antenna basically outperforms the standard design, and when you put a superstrate, that is going to significantly enhance the performance of the patch antennas. So, including a superstrate is a good thing, and again using composite metal dielectric substrates basically enables patch antennas to operate in multi-band and multi-directional modes. And what you have seen, that when you have composite substrates with multiple layer wire grids like this, you will experience a blue shift. That means the resonance frequency will shift towards higher frequencies, okay, compared to that from the one layer grid. But once again, if you see the amount of improvement that you are getting, it is too little to put this extra effort. So, we will not proceed in this direction further to increase the more number of layer grids of wire, okay, to improve the antenna performance. So, now let us look into the other aspects, something like antenna miniaturization with the help of metamaterials. So, in this topic you first understand what is ESA. Okay. These are electrically small antennas. These are basically small low profile antennas which are ideal for mobile, wearable, airborne or IoT devices. Now, what counts as small? So, you have to understand that the K alpha should be less than 1, and if you are having no ground, without a ground you should have K alpha less than 0.5. Now, here what is alpha? Alpha is basically radius of the smallest sphere enclosing the antenna, and K is basically the wave vector at that operating frequency. So, you can obtain K from this relation 2 pi by lambda. Now, what is the core challenge here is that although ESS, the electrically small antennas, can fulfill the need of compact transceivers, okay, miniaturization often reduces the radiation efficiency and the bandwidth. Okay. So, normally when you do miniaturization, the limitations such as it comes from the lumped elements, shorting pins or high permittivity ceramics. All these things can degrade the radiation characteristics. So, if you use a metamaterial approach, they basically allow you to overcome these limits and enhance the radiation properties while still maintaining a very small size, and that is why people study antenna miniaturization with metamaterials. Now, this particular reference paper, as you can see here, it is in IEEE Access. It is a review of the state of the art and the future design challenges of metamaterial-inspired antennas. So, from there we will discuss couple of interesting designs today. So, the first one is an interesting theoretical investigation regarding miniaturization of patch antennas using metamaterials, which was presented by Liu et al., their group. So, they basically used metamaterials to approach the fundamental limits of electrically small antennas. So, that allows you to see the performance versus size issue. So, earlier studies largely minimized the patch size for a certain resonant mode, but they ignored the radiation quality. So, in other words, you can say that they basically explored the characteristics and the placement of metamaterial loadings, okay, not only for shrinking the antenna's dimensions, but also for achieving good radiation properties. So, this is what Liu et al. Or their group has done, that their objective here is not only to shrink the antenna dimensions, but to also ensure that the radiation pattern or the radiation properties remain good, which was not done in the earlier studies. Okay. So, they basically considered a rectangular patch which is shown here, and they filled the bottom plane with two different materials and evaluated the resonance frequencies by applying a standard cavity model. So, here you can see that one part has got a refractive index of epsilon 1, the other one has got epsilon 2. Okay. So, this is the total width. So, eta is basically the fraction that is covered by material epsilon 1, and then 1 minus eta will be the fraction times W will be the fraction that is covered by, this is basically the width, 1 minus n is the eta is the fraction. Okay. So, this is a 3D perspective view, so that gives you a better understanding of how things are done. So, this is a rectangular patch antenna that is loaded with inhomogeneous substrate. So, here you consider a metallic patch that is having a dimension length L and width W that is placed over a ground plane, okay, that you see here at the bottom. At the height is it's given as distance h. Okay. Now, the underneath substrate that you see here is basically inhomogeneous because it is filled with two different isotropic and homogeneous material, which has got permittivity and permeability epsilon 1 mu 1, and the other one has got epsilon 2 and mu 2. Okay. So, this could also be dispersive. So, they are all function of omega. Now, eta is basically the filling fraction of the volume underneath the patch. So, eta W is basically this width and 1 minus eta W is basically this width, right. So, it is shown that arbitrary low resonance frequencies can be obtained independently from the patch dimension when the permittivities of the two materials will have opposite sign, right. So, that is main finding over here, is that if you choose these two material permittivities to have opposite sign, the effective permittivity will be very less, and that will allow you very low resonant frequencies, right. You can also extend this to circular patches. So, if you properly engineer the underlayer materials, okay, which can support efficient radiating modes similar to regular patches at smaller size. So, you can also go for circular patches. So, what do you take away from this particular exercise, that the metamaterial loading that can be done using two opposite sign permittivity pairs basically provides a path to substantially smaller patches without sacrificing the radiation pattern or radiation performance. So, that basically tells us about how you can minimize the antenna size while maintaining the radiation pattern. Now, another interesting approach for antenna miniaturization arises from the metamaterial transmission line approach. So, here you can see the dispersion curve of this transmission line, which illustrates that there is a frequency window where the propagation constant, that is beta, is basically negative. Okay. So, that is true for purely left-handed ones like this, okay, and on the other one where the propagation is purely right-handed. So, here you can actually see the dispersion curves of a composite right left-handed structure that basically combines right-handed, which is RH, and left-handed, that is LH propagation characteristics in the same medium, right. So, what you see here is that a band gap basically separates the two region, and this band gap can be eliminated, and that case can be referred to as the balanced case, since it will basically provide a more smooth transition, or you can say it provides a smooth transition between the left hand and the right hand regions. Okay. So, here the propagation constant is basically 0 at the transmission or transition frequency of omega naught, and therefore, the guided wavelength, which is obtained as lambda g equals 2 pi by beta, because beta is 0. So, this guided wavelength becomes infinity. Okay. So, this basically this transition occurs at a frequency omega naught, which is given as the fourth power of 1 over CR LR CL LL. So, these are nothing but coming from this unit cell diagram of this composite right left handed transmission line model, okay, that basically consists of series inductor and shunt capacitors, and also you have shunt capacitor and shunt inductor, okay, like this, and these two basically represent LR and CR, these are for the right handed one, and this is for CL and LL, they are for the left handed ones, right. So, it is important here to note that the propagation behavior of a this kind of composite right left hand transmission line is not purely LH even in the left hand regime, and it is not purely RH in the right hand regime, right. So, this can be also illustrated in this particular figure, where you can see there is a clear discrepancy between the curves of a PLH, okay, that you see here, and you see the curve of this composite that is in the blue region. So, they are not overlapping, and the same thing happens here as well. So, you can understand that these are not purely left hand or right hand kind of propagation, right. You can take an example of a practical implementation that is based on distributed elements, which is shown here in this figure, where you have a microstrip line, okay, this ones, okay, that is periodically loaded with interdigital capacitors, which basically have series capacitance CL, okay, and then you have this grounded stubs, okay. So, they basically give you shunt inductance, which can be considered as LL, right. So, this is a practical implementation of this composite right left handed, okay, transmission line structure. So, this is the unit cell that is shown here, the periodicity is P, okay, and this basically consists of interdigital capacitors and stub grounded inductors, right. So, what you see here is that a balanced RLH transmission line will have no band gap between the LH and RH regions, okay, and that will have infinite guided wavelength because beta is 0. So, you can have lambda g equals infinity at that omega naught frequency, right, because your beta at omega naught is basically 0. So, this can be translated into an arbitrary antenna size, since the resonance frequency is basically independent of the physical volume, and it only depends on the LC values of this unit cell. So, what happens because of that, a significant size reduction can be achieved, and this type of antennas are basically referred to as zeroth order resonator or ZOR, where this name is basically originating from the conventional transmission line mode numbering, right. So, this method was basically used by Sanada and his group. So, that is again from this paper, where they achieved 61% size reduction as compared to conventional resonators, and that was accomplished by utilizing this kind of cascaded unit cells. Okay. So, this is the unit cell which is periodically repeated, right. Similarly, here you can see an antenna with a length of lambda by 6 was proposed by them. Okay. So, similar concept was used, interdigital capacitors, then you have some Mendel line, and then finally you have some virtual ground capacitors, and this is where you put the 50 ohm input. So, this is a planar miniaturized ZOR antenna. Okay. So, these are basically the metal parts that is shown in the light gray color, same here as well. Okay. So, this Mendel line inductors were basically introduced for realization of the shunt inductance, right. So, that were replaced by this Mendel lines. Now, as far as practical designs of meta-resonator based small antennas are concerned, several miniaturized monopole variations were basically presented by Tykos and his group. Okay, and these are some miniaturized split ring resonator based monopole antennas. So, this is a standard monopole, this is the SRR that is shown here. So, this is basically complementary structure. Okay, and then you also have a L shaped monopole, and this will get a CPW feed, right. So, they basically simulated this kind of single SRR unit cell and then tuned its geometric parameters to achieve resonance in the desired band, and then placed it in the proximity of monopoles with lengths lambda by 10 to lambda by 14. Okay. So, that is the length. Now, due to magnetic coupling between the SRR and the monopoles, what will happen, the frequency of the composite antennas basically get shifted towards the SRR's resonance, that is around 2.4 gigahertz, while the initial monopole resonance, which is around 5.8 gigahertz, remains maintained. Okay. So, this is basically a graph that shows the S11 parameter as a function of frequency. This has got simulation as well as measured data. So, simulation is basically the solid line. Okay. So, here you can see you have this 2.4 gigahertz and also 5.8 gigahertz somewhere here. Okay. Now, there are two simulations done. There is another simulated curve that is with this one, the dash dot that you see here. So, that is with when there is no SRR, so only the monopole is present. So, that is around 5.5 here. Okay. And this is more or less close to 2.4, 2.5. Okay. But when you see the measured one, that is basically the dashed curve. So, that is basically matching the one with your SRR, simulated SRR, right. So, that is basically this solid curve, right. So, you are basically able to predict the performance of this antenna very well with the help of simulations. Now, what is the cause of this miniaturization that you are obtaining? First thing you can think of, that the negative permeability of the single resonator cell, okay, that is the SRRs, they cannot be regarded as the main cause of this miniaturization, since more unit cells are basically required to form an effective medium that has gotten macroscopical impact. Here only one SRR is there, and that cannot be the main factor behind all this. So, therefore, the miniaturization is basically attributed to the sub-wavelength resonant nature of the SRRs. Moreover, you can see the efficiency and the bandwidth of the antennas are acceptable, and they are varied between 0.24 and 0.48, and the bandwidth can be between 30 megahertz to 127 megahertz at this 2.4 gigahertz frequency, center frequency, right. And based on that, Dong and his group, they proposed two complementary split ring resonators, which are these ones. Okay. So, there also the structure was of complementary split ring resonator. So, and they have used a reactive impedance surface, that is RIS, along with that. Okay. So, they have got a small patch antenna with two CSRR on the patch. Okay. So, this patch is basically looking like this, and it has got a reactive impedance surface which looks like this underneath. Okay. So, they noted that while the complementary split ring resonator is a high quality factor sub-wavelength resonating structure, it radiates poorly due to the fields radiated by slots basically cancel out each other in the far field, and therefore, it basically gives you poor efficiency. So, therefore, what they have done, they considered the coupling between the complementary split ring resonators, that means the resonating cells with poor radiation with a patch which is non-resonant at the desired frequency, but it has got a good radiation pattern, right. So, this is basically the key for miniaturization here. In addition, you will see the RIS basically stores the magnetic energy, and hence it increases the impedance of the inductance of the antenna, and thus it can be used to miniaturize the size of the patch type antenna. But if you play with the inductance, your resonance frequency will decrease, because when the inductance increases, resonance frequency decreases, and that you can see here. Okay. So, by adding RIS, the resonance frequency has been moved down to 2.4 as compared to 2.75 gigahertz, which is for without that RIS case, right. So, this is basically that structure. So this patch is basically having a dimension of 0.099 lambda by 0.513 lambda. So it is very compact, as you can see, okay, and the size of the RIS and ground are basically 0.22 lambda by 0.22 lambda, this is square, okay, and then you have 0.272 lambda, that is basically the ground, okay. So by 0.272 lambda respectively. Okay. So here you also can see the comparison of S11 versus frequency. You can see the unit cell numbers of the RIS is basically changed here. So first this curve is basically for 3 by 3, then you have 3 by 5, then you have 5 by 5, then you have 7 by 7, okay. And for reference you also have, you have these two cases, that is no RIS for simulation and the solid one is a measurement curve. So these two basically tells you when the RIS is not there, and when it is there the curves basically behave like this, and you can see that with more number of elements you are basically getting shifted towards lower frequency, right. Another design was proposed by Saravi and his group. They designed a 2 by 2 MIMO antenna, that is multiple input multiple output antenna platform consisting of small CSRR based patch antennas, and this time the CSRR was etched on the ground plane, and that resulted in 76% size reduction with 29% efficiency. We will show you how it is, okay. You can also find the details in this particular paper, it is not mentioned in this slide though, okay. But you can see another design here that highlights miniaturization factor, that is proposed by Zhu et al, and it means Zhu and his group. They presented a dual band metamaterial inspired small monopole antenna. So you can see this is the monopole, and then it has got a slot, T slot with some interdigital capacitor. So this antenna was basically loaded with an interdigital capacitor and a inductive slot that you can see in the figure, and it has got very small dimensions. It is 1 by 13.3 lambda naught by 1 by 21.4 lambda naught at 2.45 gigahertz. So you can understand that this is a very small size, this is a small monopole antenna which is loaded with this capacitor and inductive slots, okay. So while the loaded monopole, unloaded one, you can use that for comparison, okay. So this is the unloaded one, these dashed lines, okay. So they do not have this dip here, as you can see, right. So the unloaded monopole antenna basically only resonates around 5.8 gigahertz, okay. It is somewhere here, yeah, this one, it is around 5 gigahertz, okay. And when you put this metamaterial loading, that means you can have this T-shaped slot that is combined with this interdigital capacitor, that basically forces the currents to basically wrap around it. So that happens around 2.4 gigahertz, and that is why you start getting this dip, and that is basically an additional radiating mode that you obtain at this lower frequency because of this kind of loading. Another design is shown here, that is by Lee and his group. So this is one of the most efficient miniaturized antennas, okay. So this is a small antenna that is loaded with ELC cell, okay, which is basically electric LC structure. So the top looks like this, and this is the bottom, okay. So you have this electric LC structure that is placed underneath the antenna, and that is basically giving you tri-band operation. You have an operation at 2.5 gigahertz, 3.5 gigahertz, and also at 5.8 gigahertz, that is band 1, band 2 and band 3, right. So the solid line shows here the antenna 1, okay, and the dotted line shows you only the monopole antenna, right. So that is used for comparison. So here what is happening, the radiating element is basically a rectangular patch which is fed by this standard microstrip line. Now because you have put this electric LC structure beneath the antenna, you are getting this tri-band operation which is important for WLAN and WiMAX application. So this is the fabricated view of this antenna, this is the top view and this is the bottom view of this antenna. The gray one shows the metallic parts, right, and this is the scale for comparison. So you were able to obtain 90% efficiency for this antenna's footprint, which was typically lambda by 6 by lambda by 10. So we can conclude that although this metamaterial ESAs have a great potential, you still require further investigations and more designs that can push the frontiers and accelerate the design process in this direction, and these are still underway and it is necessary. So with that we conclude this lecture, and in the next lecture we will continue discussing more metamaterial inspired antennas. And if you have got any queries regarding this lecture, drop an email to this email address mentioning the course name and the lecture number on the subject line. Thank you.